At the edge of existence lies a line no eye has ever crossed, a boundary both invisible and absolute. It is a horizon where light itself slows, stretching thin against the weight of gravity, until even its final glimmer is lost to silence. Time, too, bends here, drawn out into eternity, each moment unraveling as though the universe itself resists letting go. This is the horizon of no return, a threshold where the laws of physics, so carefully measured and trusted, fracture into uncertainty. For some, it is the end of being, the final curtain drawn across the stage of reality. For others, it may be a doorway, a hidden passage into realms untouched by our imagination. Here, opposites converge in haunting symmetry: eternity and finality, brilliance and darkness, existence and nothingness. To stand before such a frontier, even in thought, is to confront the deepest paradox of all, that the universe may both reveal and conceal its greatest truths in the same breath. Is this horizon, the ultimate limit of human knowledge, the point beyond which inquiry falls silent? Or is it the beginning of something vaster, where our questions dissolve only to give rise to even greater mysteries? The cosmos whispers a challenge through this frontier, daring us to look closer, to imagine further. For at the horizon of eternity, the universe asks its most profound question, not of what lies within the stars, but of what lies beyond them. If you are new here, join the journey. Like, subscribe, and let's begin. From the dawn of thought, humanity has lived with the idea of boundaries. The earliest sailors looked upon the ocean with reverence and fear, believing that at its edge the world might simply fall away into darkness. Ancient civilizations raised their eyes toward the night sky and imagined a dome encasing the heavens, a ceiling separating the mortal realm from the eternal beyond. These myths were not childish errors, but reflections of a deeper intuition, that reality must have limits, and that beyond those limits lies something unknowable. The concept of a horizon has always carried with it a quiet terror. It is the line where sight ends, where knowledge vanishes, where imagination is forced to leap into the void. For millennia, horizons belonged to sailors, to explorers, to dreamers. But in the 20th century, a new horizon was discovered. Not across the seas, not beyond the stars, but woven into the very fabric of space-time itself. In 1915, Albert Einstein unveiled the general theory of relativity. It was not merely an adjustment to Newton's laws, but a profound rewriting of the stage upon which the universe performs. Gravity, Einstein revealed, was not an invisible force reaching across space. It was space itself, bending, curving, and flowing under the weight of matter and energy. Stars no longer sat in emptiness. They carved valleys in the geometry of reality. Time itself no longer ticked uniformly, but stretched and slowed under the pull of gravity's hand. Yet, hidden, inside Einstein's equations lay something even stranger. A soldier in the chaos of World War I, far from the ivory towers of academia, became the first to glimpse it. His name was Karl Schwarzschild. In the mud of the Russian front, surrounded by the ruin of artillery fire and the uncertainty of survival, Schwarzschild carried with him not only military duties, but the restless mind of a mathematician. Einstein's paper on general relativity had just been published. Within weeks, Schwarzschild read it and began to test its implications. While shells fell across the battlefield, he calculated by hand the solutions to Einstein's new geometry of space and time. What he found was startling. The equations did not merely describe the gentle bending of space around planets and stars. They hinted at a point of collapse, a region so dense, so curved, that the very structure of reality broke down. Around this abyss, he found, a boundary emerged, a horizon beyond which nothing, not even light itself, could escape. It was the birth of the concept that would later be called the event horizon, a place where the universe drew a line and declared, beyond this, information does not return. For Schwarzschild, the solution was elegant, precise, and terrifying in its implications. He had uncovered a horizon that was not myth, not metaphor, but a direct prediction of mathematics. And, yet at the time, few could bring themselves to believe it. To most physicists, the idea seemed absurd. How could nature permit such an infinite collapse? How could light itself be imprisoned? The horizon Schwarzschild described felt less like a physical reality than a trick of the equations, a ghost conjured by mathematics, but divorced from the world of stars and galaxies. Even Einstein himself doubted their existence. He believed that nature would find some way to prevent such monstrosities, that no star could truly collapse so far as to create an invisible wall in space-time. For decades, the horizon was dismissed as a mathematical curiosity, an elegant but unreal possibility, useful for theoretical games, but irrelevant to the cosmos. Yet, the idea lingered. Like the ancient belief in oceans that ended at nothingness, the horizon Schwarzschild described haunted the imagination of physicists. It sat there, embedded in the equations, silent and waiting. The world was not yet ready to accept that the universe itself might contain such absolute boundaries. But the seed had been planted. A new kind of horizon had been glimpsed, not by poets or philosophers, but by the cold precision of mathematics. And though it would take half a century for evidence to emerge, the discovery marked the first step toward a revelation that would challenge not only science, but the very way humanity understands the meaning of limits, of endings, and of eternity itself. This was the moment when the ancient fear of horizons was reborn, not on the edge of seas, nor in the dome of the sky, but at the very heart of space-time, where light itself fades into silence. For decades, the horizon remained buried in mathematics, a quiet ghost within the geometry of Einstein's equations. It was there, undeniable, yet few dared to believe that the universe itself would ever allow such an extreme frontier to exist. To many, the notion of a surface where light itself could never escape seemed almost obscene, a violation of the natural order. Physics, it was thought, must surely forbid such infinite collapses. But the 20th century was a century of broken certainties. Relativity had already dismantled the absolutes of space and time. Quantum mechanics had dissolved the predictability of the atom into clouds of probability. Against this backdrop of upheaval, the impossible horizon began to stir once more. In the years after Einstein, a new generation of physicists picked up the trail. Among them was John Archibald Wheeler, a man whose words carried the weight of poetry, even within the cold corridors of science. Wheeler recognized that Einstein's equations, if taken seriously, did not merely describe stars and planets, they foretold something darker. He began to call them by a name that would stick: black holes. To Wheeler, these objects were not simply curiosities of mathematics. They were the most extreme predictions of relativity, boundaries where the stage of the universe itself folded in upon itself. But Wheeler was not alone in this pursuit. In Britain, a young mathematician named Roger Penrose advanced the idea further. With the unyielding rigor of geometry, Penrose proved that under the right conditions, collapse into a singularity, a point of infinite density, was not merely possible, but inevitable. In the 1960s, his singularity theorems shook the scientific world. They showed that the horizon was not an accident of Schwarzschild's wartime calculation, but a structural truth woven into Einstein's universe. And yet, even with Penrose's proofs, doubt remained. Mathematics could describe a horizon, but where was the evidence that the cosmos itself hosted such monstrous boundaries? For centuries, astronomy had been the science of light. Telescopes revealed stars, galaxies, nebulae, things that shine. How then could one ever see the edge of nothing? The answer came from the deep radio skies of the 1960s. Astronomers scanning the heavens with new instruments began to notice sources of radio waves unlike anything seen before. These were not stars or galaxies. They were compact, blazing, and unbelievably distant. The first to be identified was 3C 273, a tiny speck of light in the constellation Virgo. Through a telescope, it appeared faint, almost insignificant, yet its brightness, once measured, was staggering. It shone with the power of hundreds of galaxies, combined, all compressed into a space no larger than our solar system. The term was coined, quasi-stellar objects, or quasars. They burned like beacons at the edges of the universe, their light traveling billions of years to reach Earth. And yet, their engines were invisible. No ordinary star could account for such energy. No cluster of suns could shine so fiercely in such a small space. The invisible wall was no longer theory. It had found its signature in the sky. The only mechanism powerful enough to drive quasars, scientists realized, was the feeding of supermassive black holes. Giants millions or billions of times heavier than the sun, devouring matter in disks of incandescent fire at their horizons. Slowly, the skepticism that had surrounded Schwarzschild's ghost began to dissolve. The event horizon was no longer a mathematical trick. It was the beating heart of the brightest lights in the cosmos. From quasars to active galactic nuclei, from X-ray binaries to collapsed remnants of stars, evidence mounted that horizons were not rare exceptions, but pillars of the universe's design. Still, the horizon remained an enigma. It could not be touched nor crossed in experiment. Its edge was both there and not there, invisible and yet unavoidable. As Wheeler often remarked, black holes had no hair. They carried no features, no details, only mass, spin, and charge. To the outside world, every horizon was the same. A perfect surface, erasing all history of what had fallen in. And with that realization came a new unease. If horizons truly existed, then they were not just boundaries in space. They were boundaries of knowledge itself. For whatever crossed them, no signal could return. Information, it seemed, was lost to the universe forever. In the halls of physics, this was not a minor discomfort. It was a wound to the very principle of science. That information can be preserved, that causes led to effects, that the universe is ultimately knowable. The horizon mocked that principle. It was a veil behind which the story of matter ended, cut off from the pages of reality. As the mid-20th century unfolded, astronomers gathered more and more indirect proof. Binary star systems flickered with strange rhythms, as unseen companions pulled matter from their neighbors and devoured it. X-rays poured from these systems, evidence of matter spiraling inward towards something compact and ravenous. Cygnus X1, a source of piercing radiation discovered in 1964, soon became the first serious candidate for a stellar mass black hole. The invisible wall was tightening around the imagination of science. By the close of the 1960s, the horizon had shifted from myth to possibility, from possibility to near certainty. Quasars had revealed the monstrous scale of black holes at the centers of galaxies. X-ray binaries suggested that smaller black holes were scattered throughout the Milky Way. Penrose's theorems had shown collapse was inevitable, and Wheeler's voice had given them a name that captured both fear and fascination. The invisible wall was no longer a curiosity in equations. It had become a structure of the universe itself, one that shaped the birth of galaxies and the death of stars. And with every discovery, the horizon grew less like a distant frontier and more like a silent presence woven into the fabric of cosmic history. But though the horizon had unfolded before human eyes, it had not yet revealed its true depth. The greatest paradoxes were still waiting. The mathematics hinted at infinities. The physics strained under contradictions. And behind the veil, at the center of collapse, waited the singularity, a place where the laws of nature themselves threatened to break. The horizon was no longer invisible. It was now a wall etched into the cosmos. But what lay beyond it would demand not only new instruments, but a new imagination. The horizon was no longer a distant speculation. By the mid-20th century, mathematics, astronomy, and observation had converged upon it. Yet with this convergence came a shock unlike anything physics had ever endured. For the event horizon did not simply challenge the imagination, It defied the very intuition of reality itself. To stand before this boundary, even in thought, is to enter a realm where perception collapses. Imagine a star collapsing under its own weight, matter cascading inward, drawn deeper and deeper into the tightening grip of gravity. To the one falling, the crossing of the horizon is uneventful. The moment comes and goes without fanfare, without resistance, without the faintest sense of passing through a wall. For the traveler, space-time flows as it always has. Time moves forward. The journey continues. The descent into darkness is smooth, uninterrupted. But to the outside observer, watching from a safe distance, a different reality unfolds. As the object approaches the horizon, its movement slow. Each moment of descent appears stretched, elongated, frozen. Light from the falling body grows dimmer, its waves stretched to red by the immense pull of gravity. Colors fade, signals weaken, and then, at the very edge, light itself ceases to escape. To the distant witness, the object never crosses. It lingers forever on the brink, a ghost locked to the surface of the horizon, suspended in time. This contradiction struck physicists with unease, for the horizon did not merely bend perception, it divided reality itself. To one traveler, the crossing was instant and inevitable. To another, it was infinite and unreachable. Two truths existed side by side, incompatible yet equally demanded. By the mathematics of relativity, the deeper they studied, the stranger it became. Time, once thought absolute, was revealed by Einstein as elastic. And near a horizon, time does not merely stretch, it fractures. Clocks slow to a crawl, signals decay into silence. The universe itself seems to turn away, refusing to acknowledge what has passed beyond. This phenomenon, known as gravitational time dilation, was not fiction. It was measurable, testable, and later confirmed by experiments in the weak gravitational fields near Earth. Satellites orbiting above experience time at a different rate than those on the ground, requiring corrections to the global positioning system. What Einstein had predicted became undeniable fact. And yet, near the horizon of a black hole, this effect reaches an almost unbearable extreme. Time outside and time inside are no longer versions of the same flow, but separate tapestries, woven in different threads. Alongside time dilation came the effect of gravitational redshift. Light escaping from near the horizon is stretched, its wavelength pulled longer by gravity's grip. A flash of blue becomes red, then infrared, then radio, until it disappears into darkness. The horizon does not announce itself with brilliance. It fades into invisibility, swallowing color, frequency, and motion until only silence remains. The implications were staggering. The event horizon was not simply a location in space. It was a boundary of experience. Two observers could describe the same event in irreconcilable ways, and both would be right. For science, built on the faith of universal truth, this was deeply unsettling. If reality could fracture in this way, what did it mean to speak of one universe at all? Einstein himself wrestled with the unease. He had accepted the mathematics, yet recoiled at the idea of true singularities and inescapable horizons. He believed nature would find a way to avoid them, that the cosmos would forbid such unnatural prisons. But nature proved less gentle than Einstein hoped. The paradox was sharpened by another revelation. If nothing could escape from within the horizon, not light, not matter, not signals, then whatever crossed was lost to the universe forever. For a science rooted in causality and conservation, this was alarming. Information, it seemed, could vanish. The details of what had fallen in, its composition, its structure, its history, would never again influence the outside world. The sea horizon was not only a physical boundary, it was an epistemic one, a veil across which knowledge itself could not pass. To physicists, this struck at the heart of science. The discipline had always been a quest for continuity, The belief that nature is consistent, that nothing is destroyed without trace, that every effect carries within it the memory of its cause. But the horizon broke that continuity. It consumed without return. It erased without record. It divided not only places in space, but the very fabric of determinism. The mathematics, however, was insistent. Solutions to Einstein's equations were clear. Schwarzschild's horizon was not a mistake. Penrose's theorems showed that collapse into such a state was inevitable, and astronomical evidence, quasars blazing, X-ray binaries flickering, testified that these invisible walls were not rare. They were common. They were woven into the galaxies themselves. What disturbed physicists most was not simply that horizons existed, but that they seemed to exist everywhere. Stellar black holes peppered the Milky Way. Supermassive giants anchored galaxies across the cosmos. Horizons were not exotic accidents. They were structural features of the universe. Every horizon carried with it the same paradoxes: the division of observers, the vanishing of light, the erasure of information. It was as if the universe had hidden within itself countless doorways, each leading into an unreachable beyond. From the outside, they appeared as silent boundaries, forever unbroken. From the inside, they were thresholds that vanished the instant one passed through. For the scientific mind, trained to reconcile perspectives into one coherent picture, this was a wound. Reality itself seemed unwilling to unify. The horizon stood as a line between truths, daring anyone to say which was real, and beneath all of this lay the singularity, the point predicted at the center of collapse. The mathematics whispered that within the horizon, space-time curved into infinities, density reached beyond measure, and the laws of physics dissolved. Yet that singularity could never be seen. It lay hidden, protected by the horizon's veil. What existed there was not simply unknown, it was unknowable. This was the scientific shock of the horizon, that in a universe of laws, order, and predictability, there existed places where the very concepts of law and order ceased to apply. Horizons were not merely distant features of exotic stars. They were fractures in the very idea of reality, cracks in the mirror of the cosmos. And yet, far from deterring inquiry, this shock ignited it. The horizon became not a dead end, but a challenge. It was a call to science itself, a silent demand for deeper theories, sharper tools, and new ways of imagining existence. The invisible wall had unfolded into sight. It bent light, it stretched time, it separated realities, and in doing so, it forced humanity to confront a truth as disturbing as it was profound: that the universe may be stranger than the human mind can fully comprehend, yet it is precisely within that strangeness that the next great revelations await. For centuries, black holes remained phantoms of theory. They could not be touched, could not be seen, could not be confirmed. They existed as whispers in equations and as shadows in thought. But slowly, the tools of astronomy began to stretch beyond the visible, beyond the narrow band of light that human eyes had always depended upon. And with these new eyes, humanity began to probe the darkness. The first revelations came from the sky's invisible voices. In the 1960s and 70s, satellites carrying X-ray detectors were launched into orbit. Freed from the blanket of Earth's atmosphere, they began to reveal a universe far more violent than imagined. Across the heavens, sources of intense X-ray radiation flickered and flared. These were not ordinary stars. They were systems where matter was being pulled towards something unseen, compressed, and heated to unimaginable temperatures as it spiraled inward. Cygnus X1 became one of the first and most convincing candidates. A massive blue star danced in orbit with an invisible companion. Matter streamed from the visible star, forming a disk around the unseen partner. As gas accelerated, it grew hot. So hot that it glowed not in ordinary light, but in X-rays. Yet the source of this radiation had no visible form. Calculations revealed that only a collapsed object, a black hole, could account for its mass and its silence. For the first time, horizons announced themselves not through what could be seen, but through what was missing. As instruments improved, more of these hidden pairs were discovered. Stellar mass black holes revealed themselves in binary systems, quietly feeding on their companions. The invisible wall of the horizon could not be seen directly, but its consequences lit the skies with radiation. Matter heated to millions of degrees as it neared the brink, glowing in a desperate final release before vanishing forever. These X-ray beacons became signposts, indirect but undeniable, pointing toward horizons across the galaxy. But astronomers were not content with glimpses. The challenge grew bolder. Could the horizon itself, the very edge of no return, be seen? To look upon a black hole directly seemed impossible. By definition, nothing escapes. Yet relativity offered a clue. Light does not simply vanish at the horizon, it bends. Gravity distorts the paths of photons, curving them around the abyss. This bending creates a silhouette, a shadow imprinted against the background glow. If telescopes were sharp enough, if they could act as one eye the size of Earth itself, they might capture this shadow, the first image of the invisible wall. And so began one of the most ambitious collaborations in modern science, the Event Horizon Telescope. A network of radio observatories across the globe, from Hawaii to Chile, from Spain to Antarctica, was synchronized to act in unison. Together they formed a virtual telescope the size of the planet, capable of resolving details finer than ever before. The target was chosen, the supermassive black hole in the heart of the galaxy M87, a monster billions of times the mass of the Sun. For years, data was gathered, stored on mountains of hard drives flown by hand to central facilities. Supercomputers wove the fragments together, reconstructing what no single eye could see. And in April of 2019, the world was shown an image that once seemed impossible. A glowing ring of distorted light, bent around a darkness at its core. The shadow of the event horizon. It was more than a picture. It was a confirmation that the invisible wall was real, etched into the very heart of a galaxy. The orange ring of M87K became an icon, not only for science, but for human imagination. For the first time, the horizon had been made visible, captured not by theory, but by observation. The work did not end there. In 2022, the Event Horizon Telescope unveiled its second triumph, the first image of Sagittarius A, the supermassive black hole at the center of the Milky Way. Unlike M87's, it was smaller, shifting and flickering rapidly as matter orbited at near-light speeds. Yet the shadow was there once again, a circular silhouette carved into the heart of our own galaxy. Humanity had looked into the abyss not once, but twice, and both times the abyss revealed the same truth. Horizons are real. But the cosmos had yet another messenger. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, announced the first detection of ripples in space-time itself. Two black holes, spiraling together in a cosmic dance, collided in darkness. The violent merger shook the universe, sending waves of stretched and compressed space-time across billions of light years. By the time they reached Earth, the distortions were smaller than a fraction of a proton, yet the instruments heard them clearly. This was not light. It was not radiation. It was gravity itself, carrying the story of horizons colliding. For the first time, humanity had listened to the music of black holes, a deep cosmic resonance echoing from the merging of invisible walls. Since then, dozens of such signals have been detected, stellar mass black holes meeting and merging, their horizons joining into one. Each detection confirmed that horizons were not rare. They are common, abundant, and restless across the universe. Together, these discoveries reshaped the understanding of the cosmos. X-ray telescopes revealed the violence of matter consumed. The Event Horizon Telescope unveiled the shadow of silence itself. LIGO gave voice to horizons colliding in the dark. Each tool peeled back a layer of invisibility. Each revealed what was once thought unreachable. And yet, for all the triumphs, a haunting truth remains. What happens beyond the horizon is still hidden. No telescope, no detector, no wave of light or ripple of gravity can return from within. Horizons can be mapped, imaged, and confirmed, but their interiors remain sealed. The singularity, the collapse of space-time into an unknown state, lies beyond reach. The boundary remains unbroken. Still, probing the darkness has revealed something profound. Horizons are not empty metaphors. They are engines of galaxies, sculptors of light, composers of space-time's deepest tones. They are woven into the birth and death of stars, into the growth of galaxies, into the very structure of the universe. The invisible wall has been touched, if not crossed. Its shadow has been captured. Its collisions have been heard. Its presence is undeniable. And yet, the mystery deepens, for with every confirmation, with every observation, the horizon becomes not less strange, but more. It is a silence that speaks, a darkness that shines, a boundary that is both there and not there. The instruments of humanity have reached into the abyss and returned with echoes, with images, with whispers of truth. But what lies beyond remains, concealed, waiting. The horizon is no longer only a theory, nor only a shock. It is a structure revealed by light, by sound, by silence. It is real, and it is everywhere. The event horizon began as a boundary of geometry, a mathematical surface born from Einstein's equations. It was imagined as a silent curtain draped around collapsed stars, a line that nothing could cross and still return. But in time, this boundary grew larger than the objects it surrounded. It expanded into an idea, a metaphor for limits both cosmic and human. For in probing the horizon, scientists were not only studying the edges of space-time, but the edges of understanding itself. For much of the 20th century, the horizon was seen as absolute. Once crossed, an object was gone forever. No signal, no particle, not even light could make the return journey. To the outside universe, the black hole was perfect in its concealment. But the silence of the horizon raised its own questions. If everything that entered was lost, what became of the information it carried? In physics, information is not a vague word. It is the essential record of a system's state, the coordinates of particles, the arrangement of energy. According to the laws of quantum mechanics, information cannot simply vanish. It can be scrambled, hidden, transformed, but not destroyed. For decades, this principle and the idea of the horizon coexisted uneasily, like two maps that overlapped but refused to align. And then, in the 1970s, a discovery shook both. Stephen Hawking, working at the crossroads of relativity and quantum theory, asked what happens at the edge of a black hole when the quantum fabric of space-time itself is considered. What he found was astonishing. Black holes, once thought eternal, may not last forever. Tiny fluctuations in the vacuum of space, particle-antiparticle pairs arising spontaneously, could be influenced by the extreme gravity at the horizon. One particle might fall inward while the other escaped outward, carrying away a trace of the black hole's energy. To an observer, it would appear as if the black hole were radiating faint heat, glowing not from within, but from the horizon itself. This became known as Hawking radiation. The implication was profound. Over immense timescales, far longer than the age of the current universe, black holes could evaporate. The titans of gravity, thought to endure for eternity, might fade into nothing. What had seemed like the ultimate prison was, in fact, slowly leaking. The horizon was no longer absolute. But with this revelation came a deeper crisis. If black holes radiate away their mass and eventually disappear, what happens to the information they once contained? If the horizon truly erases the records of everything that falls inside, then when the black hole vanishes, that information is gone forever. Yet this would break the most sacred principle of quantum mechanics. The universe does not allow information to be deleted. Thus was born one of the greatest paradoxes in modern physics. the black hole information paradox. It is not simply an academic puzzle. It is a collision between the two most successful theories in science. General relativity, which governs the vastness of space and time, insists the horizon is a one-way boundary. Quantum mechanics, which governs the subatomic world, insists that information cannot be lost. Each is supported by overwhelming evidence, and yet, in the shadow of the horizon, they contradict each other. For nearly half a century, this paradox has remained unresolved. It has driven some of the most brilliant minds in science to reconsider the foundations of physics. Some argue that information must leak out slowly with the Hawking radiation, encoded in subtle correlations too faint to detect. Others suggest that the horizon itself may not be what it seems, that new physics, not yet discovered, changes the very nature of the boundary. Concepts such as black hole complementarity, the holographic principle, and the idea of space-time as an emergent phenomenon all trace their roots to this paradox. The holographic principle, inspired by string theory, suggests that all the information of a volume of space may be stored not within, but on its surface. If true, a black hole's horizon could act as a cosmic ledger, recording everything that falls inside in two-dimensional form, while the three-dimensional interior is a kind of projection. In this view, the horizon is not an eraser of information, but its guardian, preserving reality in a way far stranger than imagined. Yet other proposals challenge even the smoothness of the horizon. Some theorists argue that the boundary may be violent, a searing wall of energy known as a firewall, destroying anything that crosses. This would preserve information, but at the cost of shattering the principle that an infalling observer experiences nothing unusual at the horizon. The paradox forces physicists to choose between sacred principles, each too deeply rooted to abandon. What began as a simple question, what happens when a star collapses, has escalated into a riddle that touches the heart of physics. The horizon is no longer just the boundary of a black hole. It is the boundary of knowledge itself, a line beyond which the maps of science diverge. On one side stands relativity, elegant and geometric. On the other stands quantum mechanics, probabilistic and unyielding. At the horizon, both cannot be true, and yet the universe demands that both must be. The stakes of this paradox extend far beyond black holes. If information can be destroyed, the entire framework of quantum theory would collapse. If relativity is wrong about the horizon, then space-time itself may be built on different rules than imagined. Either way, the resolution will reshape physics at its core. The answer is not just about black holes. It is about the fundamental nature of reality. Today, physicists continue to wrestle with this mystery. Some turn to the mathematics of string theory, seeking a framework that unifies gravity with quantum mechanics. Others explore the strange landscapes of quantum entanglement, where particles separated by vast distances remain mysteriously linked, hinting at connections that may weave through horizons themselves. Still others look to the cosmos for clues, in the subtle patterns of radiation left from the Big Bang, or in the behavior of black holes colliding in distant galaxies. Every step forward deepens the paradox. Every solution seems to raise new contradictions. But in this struggle lies the essence of science. The horizon has become not only a physical boundary, but a philosophical one. It challenges assumptions about permanence, about causality, about the fate of the universe itself. It forces humanity to confront the possibility that even the laws of physics, so carefully built and tested, are incomplete. What began as a dark silhouette in Einstein's equations has escalated into the greatest unsolved riddle of modern thought. Black holes are no longer just cosmic objects. They are puzzles carved into the structure of reality. They are boundaries where knowledge itself bends, where certainty fades, and where the future of physics must be forged. The horizon expands, not only across the universe, but across the mind. It is no longer only the line between light and darkness, between escape and capture. It is the line between what is known and what is not. And beyond it, lies the unfinished story of science, waiting in silence, in mystery, and in the promise of revelation yet to come. The event horizon stands like an enigma carved into the structure of space-time, a surface without substance, a boundary without walls. Around it, matter spirals, light bends, and time itself distorts into strange geometries. Yet what lies beneath the surface of this cosmic veil remains hidden from every telescope, every particle, every thought experiment humanity has devised. When nature draws a curtain, the imagination steps forward. And so, across the last half-century, some of the most daring theories in science have risen to confront the mystery of the horizon. One of the most radical ideas comes from the holographic principle. Inspired by black hole thermodynamics and the mathematics of string theory, it proposes that reality itself may not be what it seems. A black hole's entropy, the measure of its hidden information, was found not to scale with its volume, but with the area of its horizon. This discovery, pioneered by Jacob Bekenstein and Stephen Hawking, suggested that the fundamental bookkeeping of the universe is written not in the depths of space, but on its surfaces. From this arose a staggering possibility. Perhaps the entire universe works this way. Perhaps what appears three-dimensional is, at its most fundamental level, encoded on a two-dimensional boundary. Like a cosmic hologram, the depth of reality may be nothing more than projection. If so, then the event horizon is not a wall of destruction, but a library of existence, inscribing every particle, every photon, every thought that crosses its boundary into the eternal record of the cosmos. Yet the holographic principle is only one doorway. Others turn to string theory, a framework that seeks to reconcile quantum mechanics with gravity by imagining the smallest units of reality, not as points, but as vibrating strings. These strings dance not in familiar space, but in hidden dimensions, curled tightly beyond perception. In this picture, horizons may not be smooth surfaces at all. They may be higher dimensional brains, surfaces vibrating in unseen directions, their ripples shaping the fate of matter and light. A black hole could be more than a collapsed star. It could be a window into the deep architecture of the universe, where unseen dimensions breathe beneath the fabric of space-time. But not all speculations are elegant. Some are violent. The firewall paradox, proposed in 2012, challenges one of the most cherished principles of relativity, that an infalling observer should experience nothing unusual at the horizon. According to the mathematics of quantum information, this may not hold true. Instead, the horizon might blaze with unimaginable energy, incinerating anything that dares to cross. In this view, the smooth curtain of relativity is torn apart by quantum fire, and the peaceful passage into the interior becomes impossible. The firewall is an answer to the paradox of information loss, but it comes at a price. It forces physics to abandon the idea that horizons are gentle, that space remains continuous, and that relativity's calm predictions extend to the edge of eternity. Others see the horizon not as an ending, but as a gateway. In the speculative realm of the multiverse, where countless universes may coexist in vast cosmic landscapes, black hole horizons could conceal hidden bridges. Wormholes, predicted in principle by Einstein's equations, may lurk behind horizons, folding space-time into tunnels that lead elsewhere. To fall across such a horizon might not be to face destruction, but to traverse into another cosmos, another set of physical laws, another sea of galaxies. These ideas remain highly speculative, but they capture a deep human intuition that horizons, both literal and metaphorical, are not ends but transitions, thresholds into the unknown. And then there are the attempts to go deeper still, to strip away speculation and confront the horizon with a final theory of quantum gravity. General relativity describes the smooth continuum of space-time. Quantum mechanics describes the grainy, uncertain fabric of particles and fields. At the horizon, these two visions clash. The question of what the horizon truly is may only be answered by a theory that unifies them. Some propose that space-time itself is quantized, built from discrete units like the pixels of a cosmic screen. In such a picture, the horizon might dissolve into a frothing quantum fuzz, a place where smooth geometry gives way to fluctuations of Planck-scale granularity. If so, then the horizon is not a sharp line at all, but a shimmering surface where reality itself unravels into its most fundamental code. Loop quantum gravity, one of the leading candidates for this unification, suggests that the fabric of space is woven from networks of finite loops. Horizons in this theory gain structure. They become lattices of quantum threads, storing information in discrete chunks. String theory, in contrast, imagines horizons as emergent phenomena arising from the collective vibration of strings and brains. Both frameworks point toward the same unsettling truth. The event horizon may not be what classical physics imagines. It may not even exist as a smooth surface. Instead, it may be a mirage born of approximation, dissolving into a quantum tapestry. When viewed closely enough, what unites these speculations is not certainty, but necessity. The horizon forces them. It is the place where known physics fails, where relativity's predictions of smooth curvature collapse into singularities and infinities. It is the place where quantum mechanics, with its insistence on information conservation, collides with the silence of a one-way boundary. No single theory can yet reconcile these contradictions. But each attempt, whether holographic, string-based, fiery, or multiversal, is an attempt to stitch coherence back into the torn fabric of understanding. For scientists, the horizon is no longer just a boundary of space-time. It has become a crucible where the next great revolution in physics must be forged. The same way Newton's gravity gave way to Einstein's relativity, and classical certainty gave way to quantum uncertainty, so too must today's physics yield to something greater. The horizon demands it, and in this demand lies a profound reflection. The universe, it seems, is not content with simple answers. It erects horizons not only in space, but in knowledge, daring humanity to reach beyond. Each theory is a light cast against the darkness, illuminating new possibilities, while deepening the shadows elsewhere. The holographic principle, string theory, the firewall paradox, the multiverse, quantum gravity, all are attempts to peer through a veil that may never fully lift. And yet, in reaching for the horizon, humanity discovers more than black holes. It discovers the restless nature of inquiry itself. The horizon expands in the mind as much as in the cosmos. It becomes a metaphor for every limit ever encountered, every mystery that resists resolution. And just as sailors once sailed toward the ocean's edge, only to find that the world extended beyond, so too does science move forward, driven by horizons that dissolve as they are approached. Theories may rise, fall, and transform, but the pursuit continues. For the horizon is not just the end of vision, it is the beginning of wonder. To approach the horizon is to confront the limits of vision. It is a place where light itself bends away, where certainty dissolves into silence. And yet, in the last few decades, humanity has forged instruments capable of stretching sight to the edge of the impossible. These tools are not simple machines. They are extensions of perception, artificial senses that pierce into the hidden realms of gravity and light. Through them, the invisible is made visible. Through them, the horizon itself begins to take shape. At the forefront of this quest stands the Event Horizon Telescope, not a single telescope, but a network of observatories spread across Earth, linked by the precision of atomic clocks and the patience of human collaboration. By synchronizing antennas on distant continents, astronomers created a planet-sized, eye sharp enough to resolve the silhouette of a black hole against the firestorm of its surroundings. In 2019, this global effort produced a revelation, the first image of a black hole, the dark shadow of M87 encircled by a glowing ring of light. For the first time in history, the horizon was no longer a mathematical abstraction. It was a visible structure, etched into photons, bent by gravity's strongest hand. But this was only the beginning. The Event Horizon Telescope is not static. It continues to evolve, upgrading its sensitivity, expanding its network, and pushing into new frequencies. With the addition of polarimetry, astronomers have begun to map the magnetic fields swirling around horizons, tracing the forces that launch jets of plasma across intergalactic space. Future upgrades promise sharper clarity still, images capable of resolving turbulence, motion, even the subtle flickering of space-time near the brink. Each refinement draws the boundary between known and unknown into sharper focus. Yet the horizon cannot be studied from Earth alone. Space itself must become a laboratory. The James Webb Space Telescope, orbiting far beyond the scattering veil of Earth's atmosphere, extends humanity's vision into infrared light. Though Webb is not designed to image horizons directly, it studies the cosmic ecosystems around them, the stars drawn into spirals, the dust heated by accretion, the galaxies whose hearts pulse with supermassive black holes. With its unmatched sensitivity, Webb can peer through veils of dust, tracing the feeding habits of horizons as they shape the birth and death of galaxies. And even Webb is only a beginning. Future telescopes, conceived to probe X-rays and high-energy light, will bring the immediate surroundings of horizons into view with unprecedented detail. Missions like Lynx and Athena, still on the horizon of planning, promise to capture the whispers of matter as it is devoured. But the search does not end with telescopes. Horizons can be simulated, at least in part, within the controlled environments of the laboratory. Physicists create analog black holes in Bose-Einstein condensates, superfluids cooled to near absolute zero, where quantum waves mimic the flow of space-time. In these experiments, horizons are not cosmic giants, but ripples of sound or light, trapped by artificial boundaries. In 2010, such analogues produced hints of Hawking radiation, an echo of the theoretical glow predicted to emanate from true black holes. While these tabletop models cannot reproduce the full fury of gravity, they allow scientists to test principles that would otherwise remain forever inaccessible. In the silence of the laboratory, horizons are recreated as whispers, subtle enough to probe, bold enough to inspire. Meanwhile, humanity's ears are being refined as well as its eyes. Gravitational waves, ripples in space-time predicted by Einstein and first detected a century later, have opened a new channel of perception. In 2015, LIGO recorded the tremor of two black holes colliding, their horizons merging in a final shudder of cosmic silence. Since then, dozens of such mergers have been heard, each adding to the growing symphony of the dark. But LIGO is only the beginning. Plans for LISA, the Laser Interferometer Space Antenna, will extend this hearing into the silence of space, with 3 spacecraft separated by millions of kilometers, linked by laser beams. LISA will detect gravitational waves from supermassive black holes colliding across the universe. It will hear what no telescope can see, the slow spirals of horizons converging, the deep bass notes of space-time itself being torn and rewoven. These tools, telescopes, detectors, laboratory analogues, form the frontier of human observation. Yet they cannot act alone. The flood of data they produce, vast beyond comprehension, requires new forms of intelligence to decipher. Artificial intelligence, once confined to the realm of human invention, now partners with science at the edge of knowledge. Machine learning. Algorithms sift through torrents of cosmic signals, teasing out patterns buried in noise, reconstructing images blurred by distance and distortion. Without AI, the first image of a black hole would never have taken shape. In the years ahead, these artificial minds will grow sharper, learning to decode the language of the horizon in ways human eyes alone cannot achieve. What unites all these instruments is not simply the pursuit of knowledge, but the refusal to surrender to silence. The horizon conceals, but humanity responds by inventing new senses, new languages of observation. With every technological leap, the boundary recedes. A shadow becomes a picture, a ripple becomes a sound, a mystery becomes a map. And yet the closer the view, the deeper the paradox. Each discovery reveals not closure, but escalation, new questions, sharper contradictions, more intricate puzzles waiting to be unraveled. The tools at the edge of knowledge are not just machines. They are embodiments of the human will to see, to hear, to know. They are the modern equivalents of the ancient sailor's compass, or the astronomer's first telescope, extensions of curiosity into realms where ordinary perception fails. In them, one sees not just the ingenuity of science, but the persistence of a species unwilling to accept that any horizon is final. As the Event Horizon Telescope sharpens its vision, as Webb gazes into hidden galaxies, as Lisa prepares to listen to the song of merging giants, and as quantum experiments simulate the glow of Hawking radiation in laboratories chilled to silence, humanity inches closer to the brink. The horizon is still there, still shrouded, still mysterious, but with each new tool, it becomes less an unbroken wall and more a veil, thin, fragile, trembling in the winds of discovery. And so, the pursuit continues. The instruments grow sharper. The data grows richer. The questions grow deeper. Horizons are revealed not to be ends, but beginnings. Places where vision fails, and imagination, technology, and perseverance must carry the torch. In chasing the horizon, humanity discovers not only the nature of black holes, but the nature of itself, a species defined by its refusal to stop at the edge of mystery. Not all horizons are bound to black holes. Some are written across the universe itself, vast and silent, drawn not around collapsed stars, but around the whole of existence. These horizons are not born of death, but of expansion. They are not the edges of collapse, but the edges of eternity. The cosmos is not static. Since Edwin Hubble's discovery in the 1920s, it has been known that galaxies recede, their light stretched into longer wavelengths by the fabric of space itself. At first, this expansion was thought to slow over time, gravity gradually pulling the universe back toward equilibrium. But the late 20th century brought a revelation as disruptive as any black hole. Observations of distant supernovae revealed that the expansion is not slowing. It is accelerating. Some unseen force, dubbed dark energy, is driving galaxies apart faster and faster, its nature unknown, its strength irresistible. In such a universe, horizons are inevitable. Just as the event horizon of a black hole marks a boundary beyond which no signal can return, so too does the accelerating cosmos impose a limit. Beyond a certain distance, galaxies are receding faster than light itself, not by motion through space, but by the stretching of space itself. Their light, no matter how long it travels, can never reach us. They vanish not because they fall into darkness, but because the fabric between us grows too fast for any bridge to cross. This is the cosmic event horizon, a limit drawn not by gravity's pull, but by expansion's relentless push. To look into the night sky is to peer into a shrinking window of possibility. Each year, more galaxies slip beyond reach. Each year, the observable universe becomes a smaller fraction of the whole. Already, most of the galaxies that exist are gone from sight, their light forever cut off. Only their past selves remain, faint fossils of photons launched billions of years ago, traveling ever further into silence. The thought is unsettling. The night sky seems eternal, yet it is not. In the far future, as dark energy continues its work, even the nearest galaxies will drift away. Billions of years from now, a lonely universe awaits, where only the remnant stars of the local group remain visible, and the rest of the cosmos lies beyond a horizon that can never be crossed. The ultimate horizon is not a black hole swallowing stars. It is the universe itself swallowing vision. It is the growth of emptiness, the triumph of expansion over connection. The cosmos is not collapsing into darkness. It is stretching into solitude. And yet, this horizon carries echoes of the same paradox that haunts black holes. If regions of the universe are forever beyond reach, what becomes of the information they contain? Are those galaxies gone from reality, or merely hidden behind a veil of inaccessibility? In a sense, the cosmic horizon is a mirror of the black hole horizon. Both boundaries where physics insists light can never return. Both thresholds beyond which knowledge is cut away. Dark energy, the driver of this expansion, remains perhaps the most profound enigma in cosmology. It may be a property of space itself, a cosmological constant woven into Einstein's equations. Or it may be something stranger, a dynamic field that evolves with time, reshaping the destiny of the cosmos. Some speculate it could one day reverse, collapsing the universe in a big crunch. Others imagine a phantom-like energy tearing space-time apart in a big rip. For now, all that is known is that it accelerates the horizon's approach, hastening the moment when galaxies vanish from the stage of visibility. The philosophical weight of this horizon is immense. Humanity stands at a singular moment in cosmic history, able to see a universe teeming with galaxies, yet destined for a future in which that richness will fade from view. To exist now, when the night sky still reveals the grand architecture of creation, is to live in a privileged window of time. In the deep future, the cosmos will appear small, quiet, and solitary, its true immensity forever hidden. Some ask whether eternity itself is hidden behind this horizon. If the observable universe is but a fragment, does the unseen beyond stretch infinitely? Are there structures, galaxies, or even other universes lying forever out of reach? Their light, destined never to touch our detectors, their stories sealed beyond the edge of time. The cosmic horizon does not answer. It only reminds that knowledge itself has limits, not because of lack of effort, but because of the very laws of reality. For the human mind, horizons are double-edged. They define limits, but they also inspire pursuit. To know that most of the universe lies beyond sight is not only to face loss, it is to awaken wonder. The horizon does not diminish what is known. It deepens the mystery of what lies beyond. Just as the ocean's edge once whispered of continents unseen, the cosmic horizon whispers of infinities forever out of reach, and so the universe itself becomes the final horizon. A horizon not of destruction, but of separation. A horizon not of collapse, but of expansion. It is the line where light fails, where connection ceases, where time stretches into an endless silence. It is the reminder that even eternity has boundaries, drawn not by human hands, but by the universe itself. Yet perhaps, in a way, the horizon is less an end than an invitation to imagine what cannot be seen, to accept that knowledge is finite, but wonder infinite, to recognize that every horizon, whether around a black hole or around the universe itself, conceals more than it reveals. In the end, the horizon of the universe is not only a scientific fact, it is a philosophical mirror. It shows that existence is fleeting, that vision is bounded, that eternity lies always just beyond. It teaches that to gaze into the cosmos is to gaze not only into space, but into the limits of perception itself. Beyond the horizon may lie galaxies, multiverses, or silence. What awaits there cannot be known, but it is precisely this unknowing that makes the cosmos endless in mystery. Every story has an ending, but in the universe, endings are rarely final. They are thresholds, horizons, boundaries where knowledge halts and mystery begins. From the birth of the idea of black holes in the equations of Einstein, to the dazzling images of shadows captured by telescopes, humanity has inched ever closer to the edge of understanding. And yet, at every step, the horizon has moved further away. The event horizon was once only a line of mathematics, a strange boundary drawn in chalk on the blackboards of theorists, but it has grown into one of the central symbols of modern science. It is no longer only about collapsing stars. It is about the fabric of reality itself, about the limits of vision, about the fragility of certainty. The horizon is where light dies, but also where imagination ignites. Black holes have shown that nature is more audacious than the human mind once believed. They hide entire worlds of physics inside their shadows. They defy common sense, bending time, swallowing matter, and yet whispering of evaporation and rebirth. They remind that what falls into silence may not be gone forever, that the universe plays by rules still half hidden, still waiting to be deciphered. Beyond them, the universe itself stretches toward its own horizon. Galaxies drift away there, light red-shifted into darkness, until the night sky will one day empty. This cosmic horizon is not carved by gravity, but by expansion, not by collapse, but by separation. It is the ultimate mirror, reminding that even eternity is bounded. Even infinity is framed by edges. And yet, in every horizon, there is a paradox. It is both a boundary and an opening, a wall, but also a doorway. It denies passage, but invites on thought. The horizon exists because of what cannot be seen, but it also exists because of what can be imagined. In the laboratories of Earth, physicists search for clues. They test the quantum world, build machines to detect gravitational whispers, and design instruments sharp enough to glimpse the shadows of the abyss. In the mathematics of string theory and holography, they attempt to reimagine space and time as something richer, more fluid, more profound than ever conceived. Each attempt reveals fragments, but never the whole. Each theory brings answers, but also deeper questions. Perhaps this is the true gift of the horizon. Not closure, but wonder. Not certainty, but curiosity. Horizons remind that reality is layered, that knowledge has borders, and that consciousness itself thrives not on answers, but on mysteries. For humanity, the horizon has always been the symbol of pursuit. Ancient explorers sailed toward the edge of the ocean, believing it to be the end of the world, only to discover new continents and wider seas. In the same way, modern science sails toward horizons of space-time. Each crossing reveals more vastness, more depth, more enigmas hidden in the folds of creation. The horizon of a black hole, the horizon of the universe, the horizon of knowledge itself, each one reflects the same truth. The story is not over. The cosmos is not a puzzle with a final solution. It is a living mystery, unfolding in silence, infinite in its questions, eternal in its beauty. And so, the journey does not end here. The horizon remains ahead, waiting, receding, beckoning. It reminds that to exist at all is to dwell in mystery, to live on the edge of what can be known, always gazing beyond, always wondering. Perhaps the greatest lesson of the horizon is not about space or time, not about gravity or light, but about perspective. It teaches that boundaries are not prisons. They are invitations. They are reminders that knowledge is finite, but wonder is not. They whisper that to look into the abyss is not only to see darkness, but to glimpse the outlines of truths yet to come. The horizon will always remain. It will shift. It will change. It will reveal new faces, but it will never vanish. And in that endless pursuit, humanity will find its place. Not as conquerors of the cosmos, but as witnesses to its unfathomable depth. For in the end, the greatest horizon is not out there in the stars, nor beyond the edges of space-time. It lies within, the horizon of imagination, the boundless frontier of thought. As long as there are questions, there will be horizons. And as long as there are horizons, there will be wonder. This is the story of the horizon, the boundary where science meets philosophy, where vision meets silence, where time itself meets eternity. A boundary that is not an ending, but a beginning, a place where the human spirit will always stand, gazing outward, listening to the echo of the cosmos, and asking the oldest, most enduring question of all: what lies beyond?